This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today we're diving into a fascinating patent, enhanced signal detection of optically encoded particles via FLAIR. It tackles the challenge of detecting airborne materials, a critical issue in various fields.
Indeed. The ability to quickly and accurately detect airborne threats, whether pollutants or biological agents, is paramount. This patent offers a novel approach to this problem.
It uses a cloud of microscopic sensors, essentially responsive dust, to detect these materials. But how does it actually work?
The key is illumination. Traditional methods struggle with alignment and environmental interference. This patent uses flares to illuminate the sensor cloud.
Flares. That's an unexpected solution. How does that overcome the limitations of other methods? Let's start with the sensor clouds themselves. The patent mentions deploying these clouds of microscopic optical sensors, often referred to as responsive dust. Can you elaborate on this?
These sensors, often made of porous silicon, are incredibly small. They're designed to react with specific airborne materials, changing their optical properties in the process. Think of them as tiny, targeted detectors scattered across a potentially large area. Deployment methods can range from artillery shells to specialized aircraft, depending on the situation.
So essentially you're creating a network of sensors across a potentially large area. This seems like a significant advantage over traditional point-based detection systems.
Precisely. The dispersed nature of the sensor cloud allows for detection across a wide area, capturing the spatial distribution of the airborne material. This is particularly useful for irregularly shaped clouds that might be missed by more localized sensors.
Now let's talk about the flare. Why use a flare instead of a laser or other light source?
Flares offer several advantages. First, they're self-contained and require no external power source, making them ideal for remote or challenging environments. Second, the broad spectrum of light emitted by a flare provides robust illumination across a range of wavelengths, ensuring that the sensors are effectively illuminated regardless of their specific spectral response. Third, the flare's relatively long burn time and slow descent, aided by a parachute, provide extended illumination of the sensor cloud.
So a broad spectrum is key to overcoming environmental interference.
Exactly. Environmental factors can attenuate light at specific wavelengths. A broad-spectrum light source, like a flare, minimizes the impact of these variations, making it easier to distinguish the signal from the sensors from background noise.
The patent also mentions comparing the spectrum of the flare with the spectrum reflected from the sensor cloud. Why is this important?
This step is crucial for accurate data interpretation. By comparing the reflected spectrum with the known emission spectrum of the flare, we can account for variations in the flare's intensity and spectral distribution. This ensures that any changes in the reflected spectrum are truly due to the interaction of the sensors with the airborne material, not variations in the illumination source.
And what about the optical references mentioned in the patent?
The references provide a crucial calibration point. They're co-deployed with the sensors and have a known, predictable reflectance. By monitoring the light reflected from the references, we can compensate for any environmental effects or variations in the flare's output, further enhancing the accuracy of the measurements.
Let's talk about the overall system. What are the key components and what are some potential applications?
The system comprises the sensor cloud, the flare, and a detector capable of analyzing the reflected light. The flare can be deployed from various platforms, including aircraft or artillery shells, depending on the specific application. Potential applications are vast, ranging from environmental monitoring to detecting chemical or biological warfare agents.
The ability to deploy the flare remotely without exposing personnel to danger is a significant advantage, particularly in hazardous environments.
Absolutely. The system's design prioritizes safety and efficiency, allowing for remote deployment and monitoring of the sensor cloud.
The patent highlights the use of porous silicon sensors. What makes these sensors particularly suitable for this application?
Porous silicon sensors offer a unique combination of properties. Their high surface area allows for efficient interaction with airborne materials, leading to a strong signal. Furthermore, their optical properties can be tailored to respond to specific target materials, enhancing selectivity and reducing false positives.
So you can essentially customize the sensors to detect specific chemicals or biological agents.
Precisely. The porosity and surface chemistry of the porous silicon can be engineered to optimize the sensor's response to a particular target material.
Let's summarize the method outlined in the patent. Can you walk us through the steps involved in detecting an airborne material using this system?
The method begins with deploying the sensor cloud and the optical references in the area of interest. The flare is then deployed and ignited, illuminating the sensor cloud. The detector measures the light reflected from both the sensors and the references. Finally, the data is analyzed to determine the concentration and distribution of the airborne material.
The use of a parachute to slow the flare's descent seems like a clever design choice.
It is. The extended illumination time provided by the slowly descending flare significantly improves the signal-to-noise ratio, leading to more reliable measurements.
While this technology seems promising, what are some of the challenges that need to be addressed?
One challenge is optimizing the sensor cloud density to balance coverage with the cost and complexity of deployment. Another is developing robust algorithms for data analysis to accurately account for environmental factors and variations in flare intensity. Further research is also needed to explore the use of different sensor materials and flare designs to enhance sensitivity and selectivity.
Are there any limitations to the types of airborne materials that can be detected with this system?
The system's effectiveness depends on the ability of the sensors to interact with the target material. While porous silicon sensors are highly versatile, some materials may not interact strongly enough to produce a detectable signal. Further research and development are needed to expand the range of detectable materials.
How does this technology compare to existing methods for detecting airborne materials?
Existing methods often rely on point-based sensors or remote sensing techniques that may not provide comprehensive spatial information. This system offers a significant advantage by providing a distributed network of sensors that can capture the spatial distribution of the airborne material. Furthermore, the use of flares offers a robust and cost-effective illumination source compared to lasers or other power-intensive methods.
So it's a more comprehensive and potentially more cost-effective solution?
That's a fair assessment. The distributed nature of the sensor cloud and the use of flares as an illumination source offer a compelling combination of advantages in terms of coverage, cost, and ease of deployment.
The patent emphasizes the ability to deploy the flare while remaining concealed. This is particularly relevant in certain applications, isn't it?
Absolutely. The ability to deploy the system remotely without exposing personnel to danger is a significant advantage in military or hazardous environments. The system's design allows for covert deployment and monitoring, making it suitable for applications where stealth is critical.
So this technology could have significant implications for battlefield surveillance and threat detection.
Undoubtedly. The ability to quickly and accurately detect airborne threats, such as chemical or biological warfare agents, is crucial in military operations. This system offers a significant improvement over existing technologies in terms of coverage, speed, and safety.
What are some areas where further research and development could enhance this technology?
There's significant potential for improvement in several areas. Developing more sensitive and selective sensors is a key priority. Improving the algorithms for data analysis to account for environmental factors and variations in flare intensity is also crucial. Finally, exploring the use of different flare designs and sensor materials could further enhance the system's performance and expand its range of applications.
The development of more sophisticated algorithms for data analysis could significantly improve the accuracy and reliability of the system.
Absolutely. Advanced algorithms could help to filter out noise, identify false positives, and provide more accurate estimates of the concentration and distribution of the airborne material.
What is the potential for commercialization of this technology? What markets might benefit from this innovation?
The market potential is substantial. Various sectors could benefit, including environmental monitoring, industrial safety, and national defense. The system's ability to provide rapid and accurate detection of airborne materials makes it a valuable tool for a wide range of applications.
The ability to detect and monitor pollutants in real time could have significant environmental benefits.
Precisely. The system could be used to monitor air quality in urban areas, industrial sites, or disaster zones, providing valuable data for environmental management and public health initiatives. In conclusion, this patent presents a significant advancement in the field of airborne material detection. The innovative use of a flare as an illumination source, combined with a distributed network of microscopic sensors, offers a robust, cost-effective, and safe solution for a wide range of applications.
That was a great discussion. Thank you for sharing your expertise.